All right, let's look at exercise six. This is from section 2.7. So we're dealing with implicit differentiation here. So we have this implicitly defined curve, um, 2y cubed, and so on. But we are asked to find where this either has vertical tangent lines or horizontal tangent lines. So we'll handle that in two parts. But if we want to know about the nature of the tangent lines to points on this curve, that's going to come from derivatives. Specifically, it's going to come from finding dy dx. So we need to first differentiate this function implicitly. Not sorry, shouldn't say function. Y is not a function of x here. But we can implicitly differentiate this. So we'll differentiate both sides with respect to x. So take ddx of the left-hand side, ddx of the right-hand side. All the terms on the left are in terms of y. So an implicit differentiation, we are essentially applying the chain rule in a specific way. Um, so I've done this with block diagrams before, but I'll do it again here. And I'll just do it once with 2y cubed. So we're finding dy dx, which means, we're assuming that our base independent variable is x. So what's the first thing that x goes through to become 2y cubed? The first thing that happens is it goes through some mysterious function, and that maps x to y. We don't know what this process is, nor do we really need to, but there's something that maps x to y. So even though y is not a function of x globally, like in a very small neighborhood around certain x values, we can say that y is a function of x. So the details on that are not terribly important for what we're doing right now, but this will show. I think this will help illustrate one of the consequences of implicit differentiation and why it is a consequence. So after x gets mapped or transformed to y, then what happens? Well, then it goes through another function, and that turns it into 2y cubed. So this function I'm going to call f, and I don't really know anything beyond this other than when x goes through function f, it becomes y. So y equals f of x. But then what happens to y here? Well, this is another function. I'll call this g of x, and I'll say that's equal to 2y cubed. So when something comes into this block, this function here called g, first it gets raised to the third power, and then that gets doubled. So I have my two functions here, and which means now I can take their derivatives. What is g prime of x? That is, sorry, I've made a mistake here. This should be 2x cubed. What's g prime of x? By power rule, this is 6x squared. What is f prime of x? So I don't know what this function, like what the nature of it is, but I know that if I'm going to differentiate f with respect to x, that comes out to be the derivative of y with respect to x. And all we can say is that's dy dx. So applying this now, again, we're using the chain rule for implicit differentiation. What is the derivative of 2x cubed? Well, that's 6x squared. Except I'm not going to write 6x squared because when I do chain rule and take the derivative of the outer function, I evaluate the derivative, or I find the derivative, but I want to evaluate it at the inner function, or with the input to that function. In this case, that's y. So I have 6y squared, and then I have to multiply that by the derivative of the inside function, which is dy dx. So for my first term, that derivative is 6y squared dy dx. This is the same rationale I'm going to apply to the rest of these. Derivative of y squared, first with respect to y, is 2y. Then we multiply that by dy dx. And finally, the derivative of y to the fifth is 5y to the fourth times dy dx. All right, so on the right-hand side of the equal sign, all of these terms are with respect to x. So that consideration of the chain rule doesn't really apply. So derivative of x to the fourth is 4x cubed. Derivative of 2x squared is minus 6x squared. And the derivative of x squared is 2x. So again, I want to solve for dy dx. So where is this going to be true? First, I'm going to factor a dy dx out of everything on the left-hand side. And what that allows me to do now is I can basically divide by this factor, this set of parentheses, to get dy dx. So dy dx is equal to 4x cubed minus 6x plus 2x over why do I have, oh, this is 5y to the fourth. That's why. Okay. Um, so over 6y squared plus 2y minus 5y to the fourth. Let me just give this one more scan. Make sure I didn't miss anything else. So 6y squared plus 2y minus 5y to the fourth. Okay. 6x squared. Keep dropping exponents. Okay, I think this is correct now. So here's my derivative. Now we're asked to do two things here. One is to find out where the tangent line is going to be horizontal. So what's true of the derivative when I have a horizontal tangent line? Well, that means the derivative is equal to 0. So basically, I'm taking this derivative here, setting it equal to 0. What's the only way for this to equal 0? That's going to happen if the denominator, or sorry, the numerator is equal to 0. So I'm going to set the numerator here equal to 0. So 4x cubed minus 6x squared plus 2x equals 0. Another way to think about this here is think about what would happen if you cleared this fraction. What would happen if I multiply both sides by this denominator, the 6y squared plus 2y minus 5y to the fourth? If you do that, you are going to multiply 0 by that denominator, and the denominator is basically going to get annihilated. So we have this, cubic. How can we solve that? Well, I noticed that I can factor out a 2 and a single power of x from everything. So I factored out 2x. I get 2x squared minus 3x plus 1 equals 0. And can I factor this quadratic? It doesn't factor, but I can still find the roots of it. One of them I know is this. I know that basically I can split this into two equations based on the factors. 2x equals 0 and 2x squared minus 3x plus 1 equals 0. So 2x equals 0, that gives me that when x equals 0, I'll have a horizontal tangent. So that's 1 point. What about 2x squared minus 3x plus 1? Got to use quadratic formula on that because I don't believe it'll factor. So x equals negative b, 3, plus or minus the square root of b squared, 9. Actually, you know what? I lied to you. This does factor. So let's factor it. So yeah, this should factor. So how does it factor? How do we split the middle term? Well, I need a pair of numbers that multiplies together to give me positive 2 and adds together to give me negative 3. That should be negative 2 and positive 1. And then from there, basically split this in half and factor the two left-hand terms and the two right-hand terms. I can factor out a 2x from these again. So I get 2x times x minus 1. And then if I factor out a negative 1 from minus x plus 1, I get x minus 1. Both of these have an x minus 1 factor. So finally, I can factor into 2x minus 1, x minus 1 equals 0. And what do I get from that? I get x equals a half and x equals 1. So I'm not going to promise this yet, but I have 3 candidates for where I might have horizontal tangent lines. X equals 0, x equals a half, and x equals 1. For now, I'll leave that as is. By the time this video is over, I will use Desmos to show that the points I have actually work out. But so I have three x values where I believe these are going to have horizontal tangent lines. So let me actually get a clean slide, or do I have enough room? Yeah, let's try to split this up here. So I believe I'll have horizontal tangent lines at these three x values, 0, 1/2, and 1. So the next part of this is where vertical tangent lines going to take place. So vertical tangent lines, those are points where the slope is not well defined. It is infinite. So what's going to cause us to get basically what's going to cause us to have a lack of differentiability? What's going to cause us to have a derivative that approaches infinity? That's going to come from if we divide by 0. So now, in this case, we want to look at where the denominator is equal to 0. So 6y squared plus 2y minus 5y to the fourth equals 0. Am I able now to factor anything out? I think the only thing I'm able to factor out is a y. So y times 6y plus 2 minus 5y cubed equals 0. So one factor I see for free is that y equals 0. And then I have a cubic. I would really love to know where that equals 0. But I don't think I'll be able to figure that out um, without graphing. So for now, let's do this. I believe that I found three candidates for where I'm going to have horizontal tangent lines, where x equals 0, x equals a half, and x equals 1. And so far I have one point where where I might have a vertical tangent line at y equals 0. This is a fourth degree polynomial. I could have four real solutions. Right now I have one. So let's do this. Let's back out of PowerPoint. Let's go to Desmos. I'll split screen just long enough to write this down. So 2y cubed plus y squared minus y to the fifth equals x to the fourth minus 2x cubed plus x squared. All right, so very strange curve here. Now, let's first check the horizontal tangent lines. So we said x equals 0. So at x equals 0, I believe I have a tangent line here. Can you tell me what this point is? Or you're not going to, are you? Let me maximize this a little more. So at x equals 0, so at the y-axis, I believe I have a point here. Let's do this. Y equals, what is that about? Negative 0.62. Pretty good. Good enough. So I believe I have a tangent line that's horizontal at both x equals 0 and at x equals 1. What about the other point we said was x equals 1/2? And I think I see that as well. So I have like a maximum, a local maximum here about where. Let's do y equals 0.21. Yeah, that's pretty good. But I also have a horizontal tangent line here. So I believe that our algebraic work was correct for finding the horizontal tangents. What about the vertical tangents? Where do we see those? So the only thing that we were able to find was y equals 0. So let's draw a graph, or let's draw a line for y equals 0. Y equals 0. Actually, that's not very helpful. So at y equals 0, that's where? That is at the x-axis. Do we see a vertical tangent line at the x-axis? I don't believe I do unless it's hiding, and I don't believe it is. So why don't we? And I think the reason for that is this. We go back to our algebraic work. We saw that a horizontal tangent line happens at x equals 0. But if you plug in x equals 0 to all the x's on the right-hand side here, I believe you'll get that this curve crosses to the origin. So I believe the fact it's possible for x to be equal to 0 and y to be equal to 0. So at this point where we thought we were going to have a vertical tangent line, so basically some non-zero number divided by 0 for dy dx, I believe we ended up having 0 divided by 0, which was not defined. So I don't think we have a vertical tangent line there. But remember, we have a fourth degree polynomial. So there could be 4 places where we have vertical tangent lines. And in this case, I believe I see at least 4. So basically, there's a point here on the left, point here on the right, and on either side of these kind of loops right here. I believe these are also vertical tangent lines. But those are based on polynomials that I did not see a way right away to solve those by hand, but we can see from our graph here that we do have several points where the tangent line is vertical as well.